Navies are undergoing a fundamental shift in how they project aerial power at sea. Rather than relying solely on massive crewed aircraft carriers, several countries now envision a future where uncrewed vehicles operate from leaner, specialized platforms. This new breed of drone carriers promises to deliver force multiplication with reduced personnel demands and lower costs. By deploying unmanned aerial vehicles from flat-top vessels, navies can extend surveillance, strike, and electronic warfare capabilities without risking pilots or investing in the full spectrum of traditional carrier infrastructure. The idea of a ship built primarily for uncrewed air operations emerged as UAV technology matured. Early experiments focused on helicopters and small rotary drones, but fixed-wing unmanned systems required more elaborate launch and recovery solutions. Designers quickly realized that amphibious assault ships originally intended to support helicopter-borne troops could be adapted to serve as inexpensive drone carriers. By replacing or repurposing hangar spaces and decks meant for helicopters and vertical takeoff jets, these vessels could accommodate catapult or ski jump facilities tailored for UAVs. The shift gained urgency as countries recognized that the escalating cost of manned carrier strike groups both in procurement and maintenance placed them out of reach for many of the world's mid-tier naval powers. In response, navies began to explore flat-top designs optimized for uncrewed aviation. The core attraction was a vessel that could operate autonomously flying platforms lasting dozens of hours, capable of reconnaissance, surface targeting, and even precision strikes. Such ships promised to reshape naval doctrine, enabling distributed operations and networked combat without the vast logistical tail of a traditional carrier. The evolution of this concept moved swiftly from whiteboard to sea trials, signaling a turning point in maritime strategy. Among the pioneering efforts, Turkey's TCG Anadolu stands out as a watershed achievement. Originally ordered as a landing helicopter dock to support troop transport and helicopter operations, its role transformed dramatically when Ankara lost access to the F-35B fighter program. Instead of shelving the new ship, Turkish engineers reconfigured TCG Anadolu with a flight deck optimized for unmanned combat aerial vehicles, specifically the indigenously developed Bayraktar TB3. The TB3, a fixed-wing drone equipped for both surveillance and light strike missions, was designed to operate from a ski jump ramp without a catapult. In early 2025, the first fully autonomous sorties from TCG Anadolu demonstrated the concept's viability. The TB3 conducted takeoffs, flight maneuvers, and recoveries in the Gulf of Saros without human intervention. For consecutive successful missions validated onboard software, deck handling, and the ship's remote command systems. By the time the TB3 logged its 100th sortie in June, Turkish naval planners had clear evidence that a vessel of this class could deliver carrier-like operations at a fraction of the cost and personnel footprint. TCG Anadolu's redefinition from a helicopter carrier to a drone bastion showcased how existing platforms could be repurposed. Turkish engineers retooled hangars to house multiple UAVs, installed automated refueling stations, and integrated data links to relay video feeds in near-Euro real-time to shore-based command centers. The vessel's commanding officers quickly understood that by leveraging autonomous systems, they could maintain continuous situational awareness across hundreds of nautical miles without deploying a single manned fighter. In doing so, TCG Anadolu became the vanguard of a new era, signaling that the balance of power at sea could shift toward those willing to embrace unmanned innovation. Half a world away, China took an even more ambitious route. In late December 2024, the People's Liberation Army Navy launched the first of its Type 076 class vessels, named Sichuan, explicitly designed to operate fixed-wing UCAVs. Unlike TCG Anadolu's ski jump ramp, Sichuan features an electromagnetic catapult system and arresting gear technologies borrowed from larger supercarriers but scaled down for drone operations. Its displacement of roughly 40,000 tons positions it between a light carrier and a landing platform dock in sheer size. Engineers configured dual islands on the flight deck to manage air traffic and sensor arrays, echoing lessons learned from both the Liaoning and the emerging Type 003 supercarriers. The ship's hangars accommodate stealthy GJ-11 sharp sword drones, which blend low observable design with strike payloads. These UCAVs can carry precision-guided munitions or extended-range reconnaissance pods, enabling Sino naval doctrine to push power projection across the South China Sea and beyond. Catapult launches allow the sharp sword to take off with heavier internal fuel loads, extending operational radius. Upon return, arresting wires capture the UAV safely, even in rough seas. The integration of such systems required extensive cooperation between aviation and naval bureaus. Designers installed reinforced flight deck plating to withstand intense catapult forces, while onboard electromagnetic generators supply power spikes in milliseconds, a feat once limited to full-size supercarriers. With hangar space designed for rapid refueling and quick turnaround, Sichuan exemplifies how China intends to scale uncrewed aviation in numbers. Senior PLA Navy strategists view the vessel as a bridge between legacy platforms and future all-drone fleets. At sea, Sichuan's radar arrays maintain constant tracking of incoming aircraft and ships, feeding data into a networked command cloud where Fleet Command can assign missions to any deployed UAV. This approach makes Sichuan a force multiplier. A single ship can dispatch multiple UCAVs on staggered sorties, maintaining near continuous presence over contested waters. Unlike traditional carriers that rely on large numbers of crew and escorts, Sichuan's design optimizes automation from deck handling robots to automated engine diagnostics, reducing crew complement by nearly 30%. In doing so, the vessel not only changes force structure but also signals to regional navies that the future of carrier operations will be written by those who master unmanned systems first. Iran's decision to convert a commercial container ship into a drone carrier revealed another dimension of uncrewed naval aviation: asymmetric power projection with minimal expense. The Shahid Bagheri entered service in February 2025 after a rapid retrofit in Bandar Abbas. Instead of building a new hull, Iran's Revolutionary Guard refitted an existing container vessel with a ski jump ramp angled off the bow, reinforced hangar decks, and refueling stations tailored for UAVs. The ship now deploys upwards of 60 surveillance and strike drone ranging from small quadcopters to fixed-wing models resembling the Mohajer series. One of the most notable additions is a stealthy, torpedo-shaped UAV capable of loitering beyond the horizon to identify targets and relay coordinates back to Bagheri's command center. The retrofit included vertical launch tubes for surface-to-air missiles and surface-to-surface cruise missiles, giving the vessel a modest self-defense envelope. Yet its true strength comes from numbers. Dozens of low-cost drones can overwhelm enemy sensors through swarm tactics. When each UAV costs a fraction of a fighter jet, Tehran's maritime planners believe they can saturate adversary defenses, gather intelligence, and even execute precision strikes without risking pilots. The Shahid Bagheri's crew complement remains under €100, most assigned to maintenance bays that resemble a makeshift drone factory. Automating data links allows flight controllers ashore to command sorties beyond Iran's littoral. Commanders view Bagheri not as a traditional carrier but as a forward-deployed swarm node, where hundreds of uncrewed platforms swarm in patterns that traditional surface combatants struggle to counter. Portugal's forthcoming NRP-DE João-2 illustrates how mid-sized navies are designing dedicated, multi-purpose drone motherships from the keel up. Set to enter service in late 2026, this 120-meter vessel features a 94 by 11-meter flight deck capable of handling everything from rotary-wing UAVs to fixed-wing reconnaissance drones launched via catapult. Its hangar spaces integrate modular bays for aerial, surface, and underwater unmanned systems. In practice, this means DE João-2 can launch an autonomous seaplane to map seafloor topography, dispatch a small USV to inspect subsurface pipelines, and deploy rotary drones for vertical surveillance, all in the same sortie window. Helicopters remain on board for crew transfer or emergency extraction, but planners emphasize that manned aviation is secondary. The ship's data center processes real-time feeds from all drones, fusing information to generate a unified maritime picture. Emphasis on automation extends to deck handling. Robotic arms lift drone pallets, refuel systems operate under automated schedules, and RE algorithms predict maintenance intervals. For Lisbon, this vessel serves dual roles: scientific research for Atlantic fisheries and defense patrols in the Iberian Exclusive Economic Zone. Portugal anticipates that by operating DE João-2's unmanned complement, its navy can enforce maritime law, conduct anti-piracy operations, and assist allied NATO task groups without deploying costly frigates or corvettes. Analysts note that its relatively small size, with a crew of just 75 specialists, reduces operational costs while maximizing mission flexibility. In essence, Portugal leveraged uncrewed systems to offset limited manpower and budget constraints, making DE João-2 a model for small but technologically agile navies. Technical innovation underpins every modern drone carrier, and nowhere is this clearer than in launch and recovery systems. Though TCG Anadolu relies on a ski jump ramp suited for TB3 drones, platforms like China Sichuan and Portugal's NRPD João 2 demand catapult and arresting gear tailored for fixed-wing UAVs. Electromagnetic catapults, EMALs, generate precise force curves to accelerate craft weighing several tons to flying speed in mere seconds. The same deck that houses powerful power converters for EMALs also hosts arresting wires that decelerate returning drones with minimal stress on landing gear. Integrating these systems on hulls under 40,000 tons required extensive structural reinforcement and engineering challenge that domestic yards solved by weaving carbon fiber composites into flight deck plating. Underneath, hydraulic dampers and shock absorbers protect delicate avionics during landings. Designers also incorporated advanced deck decontamination systems to clear hydraulic fluid or fuel spills, quickly ensuring that multiple UAV launch recovery cycles can occur in rapid succession. Royal Navy trials under Project Vixen provided key lessons. Deck surface friction coefficients must align precisely with UAV tire compounds to prevent skidding, while wind over deck calculations must account for UAVs that lack the same tailhook tolerance as manned jets. João catapult is a derivative of Vixen's linear motor design, stripped of excess mass and calibrated for drones weighing 1,500 to 5,000 kilograms. In parallel, China Sichuan demonstrated that pairing EMALs with reinforced arresting gear could yield 30 sorties per day per UAV squadron, numbers that dwarf earlier estimates. Onboard power distribution also required innovation. Single-point electrical failures could cripple a drone carrier's entire flight schedule, so engineers built redundant bus systems with smart breakers that isolate faults in milliseconds. Beyond mechanical innovations, data links evolved to support dozens of simultaneous UAVs. Carrier air traffic control now resembles a mesh network where each drone broadcasts status updates to every other asset and land-based ground stations. If one node is jammed, the system reroutes commands through alternate paths, preserving mission integrity. The network also integrates electronic warfare payloads that allow certain UAVs to act as airborne decoys, luring radar-guided missiles away from high-value assets. Within these systems, RE algorithms schedule drone takeoffs to minimize deck congestion. They assess sea state, wind speed, and projected mission length to sequence flights with brutal efficiency. The result is a drone carrier that functions as a self-aware node within larger naval task groups, capable of autonomously managing its aviation cycle. By converting legacy hulls, engineering bespoke catapults, or building dedicated unmanned motherships, states as diverse as Iran, Portugal, and China underscore a shared reality: the future of carrier warfare will center on uncrewed systems. Technical breakthroughs in launch recovery hardware and resilient networks enable these vessels to operate far beyond shores ebbed by aging manned carriers. Drone carriers change strategic calculus by shifting risk from humans to machines. When a vessel can dispatch a swarm of UAVs for surveillance or strike, adversaries face uncertainty over where threats will appear. Commanders recognize that traditional choke points lose value when unmanned assets can loiter for days, feeding real-time imagery to distant fleets. Instead of sending a manned reconnaissance plane into contested airspace, a drone carrier launches uncrewed aircraft that return only at mission's end. This reconfigures deterrence. States must now counter persistent, low-cost sensors rather than occasional overflights. In practice, deploying a drone carrier off another country's coast means intrusion detection systems may see dozens of small radar signatures rather than a single jet. Even if defenders shoot down several drones, dozens more remain. In short, persistence and attrition favor the drone carrier operator. Budget planners find drone carriers compelling because they promise high returns on modest investments. A supercarrier costs tens of billions, plus escort costs for destroyers and replenishment ships. By contrast, a drone carrier, whether repurposed or lightly armed, can cost a few $1 billion, with crew sizes under 100. Maintenance focuses on modular WAV bays, rather than catapult overhauls or life support systems for air wings. When a TB3 or GJ11 is lost, replacement costs measured in millions, not hundreds of millions, limit budget shock. Navies understand this. Turkey rechanneled funds saved from F-35B cancellations into TB3 production lines. Portugal avoids launching full-size carriers by investing in João modular WAV hangars. Iran sidesteps sanctions by retrofitting existing hulls. Each program illustrates how modest budgets can field sea-based strike and reconnaissance capabilities once reserved for great powers. Over the next decade, analysts expect mid-tier navies to allocate ever larger percentages of their maritime budgets to WAV-centric platforms. Yet vulnerabilities accompany low cost. drone carriers lack the armored decks and multi-layered air defenses that protect crewed carriers. A well-coordinated missile salvo, or anti-ship cruise missile barrage, could incapacitate deck facilities, grounding use for days. Adversaries could exploit the fact that a drone carrier's value depends on sustaining a high sortie rate. A single lucky strike against power distribution nodes can halt drone operations, even if the vessel remains afloat. Naval planners admit that a drone carrier requires a protective screen, frigates, air defense cruisers, or surface-to-air missile batteries. Otherwise, it risks being an easy target. In open ocean, this screen can adapt to emerging threats, but in littoral zones where missile ranges and geography favor shore-based batteries, a drone carrier must operate under constant threat. Commanders must balance the cost savings of the platform against the expenses of escorts and air defense upgrades. Effective use of drone carriers also depends on resilient C4ISU networks. A carrier may launch dozens of UAVs, but without secure data links, those unmanned systems become vulnerable. Adversaries invest heavily in jammers that can disrupt control signals beyond visual range. To mitigate this, drone carriers embed multiple communication arrays, satellite terminals, line-of-sight radios, and high-frequency relays across their decks. Each WAV can switch between networks if one path degrades. Commanders program mission parameters into onboard flight computers, enabling drones to continue operations autonomously if cut off from the mothership. Yet complete autonomy poses its own risks. Unethical actors could hack autonomous protocols, redirecting drones toward civilian vessels or friendly bases. Consequently, navies also adopt cryptographic safeguards and RE-driven anomaly detection to verify WAV behavior. Even so, balancing autonomy with security remains an unresolved challenge. Interoperability with allied forces presents another hurdle. While Portugal's drones share NATO-compatible data links, China's GJ-11 and Iran's Stealth WAV use proprietary protocols. In coalition exercises, allies often must establish temporary gateways between networks, an imperfect solution that risks data latency. Without full integration, drone carriers may operate in parallel with allied fleets, rather than as a seamless component. Standardizing fueling, arming, and recovery procedures across different WAV models adds complexity. Some navies explore universal drone pallets that fit into any mothership's hangar, but these remain experimental. Until interoperability matures, coalition power projection will rely on a patchwork of national drone carriers, rather than truly integrated task forces. The next generation of drone carriers will extend beyond mere flat tops. Engineers are already trialing drone barges, uncrewed hulls that sail autonomously, acting as forward bases. These barges launch UAVs without risking a crew, serving as mobile sensor networks hundreds of miles from home ports. Commanders envision entire flotillas of drone barges scouting ahead of manned carrier strike groups, generating targeting data in real time. Should a contested island chain resist, uncrewed barges could anchor closer to shore, conducting high-risk missions while relocating if threatened. In parallel, designers plan hybrid carriers combining manned fighters with unmanned wings. These vessels feature conventional catapults and arresting gear, but also house dedicated WAV squadrons. By mixing human judgment with machine endurance, hybrid carriers aim to capture the best of both worlds. Such ships will likely emerge in the 2030s as budgets recover and technology matures. Strategists debate how doctrines must adjust. Traditional carrier strike groups rely on layered defenses and concentrating firepower through manned jets. Drone carriers, in contrast, demand dispersed operations and networked architectures. Leaders must decide whether to center future fleets around autonomous vessels or continue investing in legacy platforms. Some advocate for a mothership-centric model, where drone carriers serve as the primary offensive node supported by sensors and loitering munitions. Others argue that unmanned systems supplement rather than replace manned carriers, acting as force multipliers rather than force substitutes. These debates will play out as new systems enter service. If drone carriers prove their worth in exercises and real-world operations, navies may reorganize fleets entirely around uncrewed wings. The key question remains: how quickly can doctrines evolve to harness these capabilities before adversaries catch up? Ultimately, drone carriers represent a transformative step in naval warfare. By exploiting autonomous systems, they allow rapid adaptation to evolving threats. Their limitations, vulnerability to strike, reliance on data links, and interoperability challenges underscore the need for careful planning. Yet every navy that fields a dedicated drone carrier gains valuable lessons. From Turkey's TB3 sorties to China's EMALS trials, Portugal's multipurpose design, and Iran's asymmetric swarm tactics, a new playbook for maritime dominance is taking shape. Those who master it first will shape the balance of power at sea for decades to come. Thanks for watching, and if you found the video helpful, put a like below and subscribe. See you on the next one. Peace.